Hello, everybody, and a warm welcome from Kaiserslautern, which is in the southwestern part of Germany. My name is Daniel Dengal. I'm a product manager and working for fleXstrictures, product manager of one of our solutions, which I will introduce in a few minutes. Today, I want to talk about physics-based wiring harness design and validation 36 months before SOP. So let's start with an overview, what I want to talk about today. First of all, I want to introduce us as a company, then speaking about the requirements of the industry and our customers about the motivation of these topics. Third, I want to introduce some application cases for the design and validation of flexible components, which should show you what the solution is about. And at fourth, and the main point of the presentation will be a new level of productivity inside this wiring harness development process. And last, I will conclude with a final slide. So let's start with the introduction of the company. We were founded in 2012. So this year is actually our 10 years anniversary. And we were founded as a high-tech spin-off of the Fraunhofer Research Center, which is the biggest research center in Germany. And now we are an independent research-driven small and medium enterprise. On the right side, you can see a few selected R&D projects we were or are involved. These are just an abstract. We are involved in a lot more and still working closely together with our research partner, the Fraunhofer Institutes. We are the leading company in designing and validating flexible components in real time. This means we are doing these tasks physically correct and as fast as possible, which means in real time. The solution, IPS cable simulation, is globally used for more than 130 customers from various domains. I will show a few videos of that in one of my next slides where this application plays a role. And we want to bring a revolutionary technology to an innovative 3D electrical system development process with a living digital twin. And on the right side, you can just see a few of our selected awards, which we won in the past years. So what are the requirements? What are the main requests and the wish list of, in this case, automobile OEMs? But I guess they also play a role for any other OEM, which also belongs to our customers. So first of all, when developing an electrical system, you want to reduce or develop without hardware prototypes to have a reduction of cost and development time, and to do these kind of tasks or to eliminate or at least reduce the hardware, you need to have a virtual, reliable way of validating and simulating these flexible components like wiring harnesses, cables, or hoses. A rule-based design means you do not need to be relied on the experience of the engineer. Of course, this helps, but you would like to have a process which accounts and which is capable of doing for any kind of design engineer, and you do not have any user-dependent results. As next, speaking about the process, you would like to avoid manual processes, a strong automation in development. So you need to be integrated in the IT landscape and in the processes of the customers, meaning not having manual working tasks like exporting cut files, importing again into the system, saving the results, getting it back to the cut systems or the design engineers. You want to be integrated and having a consistent integration into the IT landscape. This at the end, of course, leads to a comprehensive, consistent digital twin and also meeting future requirements such as electrification or automated driving. These requirements and these requests, of course, we know and heard from our customer itself, but also from specific events and conferences mentioned here. These are the big wiring harness conferences, most likely in Germany. So how to achieve a realistic 3D representation of these cables and hoses and wiring harnesses? First of all, starting on the left side with our software solution called IPS. It's a special tailored nonlinear model working in the background, which provides accurate and fast simulations. So you are able to do these investigations in real time, interactively, and easy to use. Second step on this solution is a comfortable way to do a measurement of these flexible parts. So we developed together with our partner a measuring system called Mesomics, where you're able to identify the mechanical properties of these flexible parts, use them as an input parameter, and then having the simulation, the software to use these parameters and being able to apply a correct behavior of these flexible parts inside a software suite. So thanks to BMW, we are allowed to show this result of an overlay of a scanned data from reality and the simulation result. And here the maximum deviation was just 0.2 millimeters. So a great result, and thanks again, we are able to show this here. What are the areas of applications? Where can you use such a tool and where it's maybe necessary to use it? Actually, every flexible is a candidate. So if you look at the top row, this is strongly relates to the automotive industry, such as wiring harness task, hoses like brake hoses, as seen in the picture, but also bellows and grommets, other flexible parts in the engine compartment, in the door grommet, the hatchback grommet, but also for future or also current developments like electrifications, such as the high voltage cables. In the lower row, which I actually want to start with a few videos in a second, of course, flexible parts also play a role in these domains like construction, agriculture machinery, railway vehicles, motorbikes, or also white goods. So let's have a look and see if this video's running. Yeah, it is. So here you just see 4 different applications. I don't want to go into detail to every single one, and hopefully this is running quite smoothly. But you can see in all of these domains, like in the upper right at construction machinery, designing and interactively changing the orientation of a fitting, for example, as you might see in a second, interactively changing this orientation, being able to investigate movements and motions, which belongs to these cables, designing motion envelopes where you're able to investigate the behavior of these flexible parts, bringing this back as a result to your process or to your CAD system. And this is all possible in these different domains. I will go a little bit more into detail on these different requirements in further examples. This should just be a first overview. Okay, the main focus of my presentation should be the automotive industry. And here I want to just go through the process from start to end and to different departments where our solution plays already a role and where our customers are already working with the software. So here we basically go from concept phase to after sales, mentioning the powertrain and chassis area on the left side with different examples like engine wiring harnesses, generator wiring harnesses, the coolant hoses, air conditioning hoses. In the chassis area, sensor cables and brake hoses, but also the cardan shaft bellow. Going further in the process in the wiring harness design and validation, also being able, as you can see in the center video, investigating door harnesses with its tolerances, also being able in these steps and inside the software to apply a VR solution, which is integrated in the software, checking things directly and investigating things in VR throughout the process until assembly and production planning with the right videos, checking an assembly of an infotainment system with the requirements on the cables and the digital human. or the human itself. Okay, I go to the next slide, mentioning a few success stories coming from our customers. First one is a success story from Honda, where they had a presentation at one of our conferences. And here in the graph, you can see the improvement by changing the validation just physically to a virtual way. So in this case, the time could reduce to 1/3 of the development time with the usage of our tool. Second story I want to mention here is significant saving of hardware prototypes and expensive design changes with an change from hardware to a simulation way approach. So in this pilot project, a brake hose and 6 sensor cables of the chassis area, they investigated a design concept with IPS 2015 and almost applied almost identical series production in 2018. So they found a major routing concept 3 years prior to SOP. And when you think of all the changes you apply during this 3 years development phase, not only related to cables, but also the connectors belonging to them, different other surrounding parts. This is a great result, being able to have a reliable, validated cable concept 3 years prior to SOP. So let's have a look at the conventional wiring harness process. Starting from the left side, from the electric information. Here it's of course quite simplified. I guess most of you are totally aware of this process, but checking the quite simplified one, starting on the left with the electric information, going to the mechanical information. Of course, this is most likely done in parallel, but as I mentioned, just showing here quite simplified. Having a spot in between, which I will come to in a second, going to the drawing of the electric wires, to the production on the form board, and at the end, a physical validation at these steps. So let's see some errors occurring along this process, and especially on the second one, the potential for unrealistic layouts doing these investigations just in the CAD system. As you might have seen in the videos I already showed, these behaviors with moving parts, you are not able to investigate this in a CAD system. So you would need to lay out flexible parts in a lot of different steps, but not being able to check this coming within motion, and therefore it can lead to unrealistic layouts. Going further in the process, from the drawing to the form board, there could be information loss like torsion, which could lead to wrong production of the wiring harness at the end. And finding out these problems and these issues at the physical validation can, of course, lead to late changes and, of course, expensive changes, which could threaten the SOP. And finding out the changes there means you need to go all the way back to one of the first steps, doing design changes, and then going through the steps of the process again. So there is a gap, as already shown, of this digital validation approach, and also already doing a correct design in the second step of this process. So let's see what our approach is. We would like to go a new way with an integrated digital wiring harness and development process, starting from the second step of this graph seen here. So let's make a little bit space to show and discuss our solutions providing in these phases of the process. So first of all, we would like to change the second part, going away from just using a CAD system to a physics-based design. So mentioning in one of my slides before that we have the possibility to do a correct, physical correct simulation of these flexible parts, we would like to go to the way to do a physics-based design and then a digital validation. Along with that, there is a possibility to do automated 3D layout, investigating several criteria and several process steps at once. And going the way until the assembly validation, where flexible parts like installing an infotainment system and the human is playing a role. So we can also check what the worker needs to do if the worker is able to do the task in data phase of the process. And now I would like to go through these process steps step by step and one after the other, starting with the physics-based design and digital validation. So in this phase of the process, you might ask, why is simulation superior to physical testing? With this approach and being able to do these things in early phase of the process, you have various tasks you can solve already. You are able to vary and interactively the length, the positions, the orientations in second as a user. You have the possibility to take the tolerances into account, feed this information back in the process if, for example, some contact avoidance plays a role. But maybe let's have a look at the next at the video, where I will go through these process steps in the example of an engine compartment. So first of all, you see with these few points, we want to create and design a cable in the software itself. So therefore, we just route or create the cable out of database. Here you see the way it should go. And then with a few next steps, you will see the cable created in the simulation. Directly visual with, in this case, the bending radius applied, being able to interactively adjust the length at all parts of the cable, being able to have an investigating the influence of the orientation of a cable socket or any other connector, and also the tolerances, such as the manufacturing and assembly tolerances. Of course, this is now a video you are seeing, but this is also we are also able to investigate these things in a very short time in the software itself. Here we would like to find the natural or most natural orientation of the clip, and you get immediate feedback on the cable itself. And next, in the video, starting in a few seconds, we would like to show an additional use case with the high voltage cables. Here we are adjusting the length to avoid collision. So you see this near spots in yellow, but in a few seconds you can also see where it leads to collision. Because in addition to the length change, we also want to define the best possible spot and connection of this clamp and validate the tolerances of this clamp. And being able to move these parts within contact handling and their physical behaviors of the high voltage cables, you can do this in a short time frame. Here you can see the collision detection. And of course, this is something you would like to avoid. So to keep away from these distances. And this is just the final result where you're able to investigate even further with some plots and some analyzers you can do with any kind of measurements such as forces, stresses, bending radius, collision detections, and going into detail with these kind of 2D plots. Okay, going to the next step of the process, the automated 3D layout. Here the question is your design ready for the SOP? You basically, with a simple change, it leads to a completely new approach. So you would specify the requirements up front and let the system do the task and leading to a satisfying layout for the cables by its own, without any user change to find and to get the best possible positions and orientation of the connectors and the clips. So seeing this video, you would just as a user define the parameters which are allowed to change, which are the clips shown here and the cable length. And in white, you can see the cable before the changes, before the optimization, and the striped red cable is the improved one, which does not lead to any contact, to any deformation or bad deformation on the cable, and providing a best possible result. And think about this task where as a user you have various possibilities to define this, and of course also various errors which could lead at the end to problems. Letting the system just do the task for you and getting reliable results at the end is of course a great improvement and an automated way to do this 3D layout. Here we are at the step to do an interdisciplinary collaboration in real time, being at the last step of our process where we would like to check assembly validations on the wiring harnesses, but of course the worker at the end also plays an important role for these kind of tasks. So let's have a closer look. Here the question is, does your wiring harness get damaged by installation? So you could detect serious cable damages due to kinking, get the shortest necessary overlength, as you also see in the video running on the left, installing the connectors one by one, also identifying the correct installation order, and interactively being possible to change the length if the cable is not long enough. And at the end, also identifying the correct way to assemble it, because here it could already lead to a failure if, for example, a right or left-handed person twists the connector the wrong way, as you see here visualized with these stripes. And you might have recognized this jump of the cable, which shows the realistic behavior. And throughout this process, twisting the cable 180 degrees the wrong way could already lead to a failure. And this process step and this investigation, you're actually not even able to investigate at the hardware, because you're just not able to see behind the infotainment system, as you're able to check currently by just looking in a simulation way approach what's happening in the background, also while installing. Checking the video on the right, of course, the worker at the end also plays an important role. You, now it is running. You might also want to know, as I mentioned already, if, for example, the worker needs to do the assembly with the right hand or the left hand, if the worker can reach the spot, if it's necessary to see something, and observe the cable behavior actually in a blind spot, which you might not see. So let's have a closer look on the next slide, how to consider this worker, this human being, in the early phases of the process. First of all, I want to speak about why it is important to check these tasks for assembly, manufacturing, and servicing. So you have various tasks where the human being plays a role, such as hand and tool access studies. Is the worker able to reach something with its hand? Is a tool necessary? What is the weight of the tool? Does it have an influence of the behavior, of the ergonomics of the human being? The field of view, is it necessary to see something? Could you do a blind assembly? And last but not least, the ergonomics, speaking about the different behaviors, the different positioning of the mannequins throughout processes. And also checking, for example, the height of a maintenance or an assembly task. Okay, so we identified a demand to integrate a digital human model in these process steps, because nowadays in industry, there's still a high amount of manual work tasks, and imagining to do these ergonomic assessments and on a physical prototype, it can lead to only being able to do minor modifications. If you check the picture in the lower right, investigating a task and identifying an error, you would need to go all the way back to design, do design changes, investigating again, or investigating several humans and several workers with different body heights and different body sizes. You need every single worker to investigate these tasks. Doing this in a simulation where you approach early in the processes, you can check this in a very short time frame. And speaking of this, there are, of course, various challenges. So the challenge for a digital model depends strongly on the complexity of the human being itself. When you imagine the high number of degrees of freedom and being able to solve an identical task in many different ways, so grasping something as a human, of course I do it just intuitively, but applying this in a simulation way, it can just be applied in many different ways. So therefore, in classical human models, joint angles and postures often have to be defined by hand. And we are taking a new approach with IPS IMA, which stands for Intelligently Moving Mannequin. The intelligently basically means you just define what the human should do, for example, grasp, or look at something, or follow a motion, and the posture calculation and the posture prediction is all handled in the background. So we created a realistic digital human model to simulate and predict human motions and behaviors to avoid late changes in the process. In this video, you can see a first step. So finding out the collision-free path of this control unit, investigating with the human being. So there's two results. The object can be assembled with a collision-free path planning, and you can check if the human being is able to do the task. In the second step, how you would work with this solution is to consider the human diversity. Thinking back of the slide I showed with the hardware, with the door, you do not have this possibility, or you bring every single worker to this hardware and identifying if it's possible. And in the solution we provide, you can check this at once. So you create a simulation with one mannequin and just use several so-called family and having validated results throughout a complete data set and database of different workers, not only checking the smallest or shortest person, but also investigating everything happening in between, and also investigating, for example, a tall man or a tall woman with shorter arm, which of course plays a role. And you would like to investigate if it's possible for everybody. The last step, or one of the last step, is the analysis. Here I just showed ergonomic evaluation you are able to investigate. This is also shown in a video. So here it's a reachability check in a very narrow space and investigating the different heights, different assembly heights. And on the right, you can see the improvement by changing the heights further low. At the last step, you see criteria 1 remains red, which actually makes sense in this case because it's the left upper arm. And with this information, you could go back to or you could provide this to the ergonomist, and who would do an further investigation of these tasks. But again, here we are still early in the product development process, and using these tools and these capabilities, of course, just is one step back if you investigate errors and still being able in a short time frame to do these design changes. Okay. So now I would like to show combining all of this in one step. So you might remember I opened up the process a little bit, but of course, this should not show that it takes a lot of time, but just showing our different solutions. So being able to do a design, an optimization, and a validation in one step should be this combined in our hub solution. You might remember the success story speaking about 75% of time savings. Here I mentioned 80% of saving in development time, and having a 3D master and a digital a living and validated digital twin at the end. So let's see how this can be applied. As mentioned before, we are going away with a new level of productivity with an integrated digital wiring harness development process where we are able to generate a complete, flexible, and physical correct wiring harness automatically in seconds. And we are having a seamless integration into existing processes and customer databases. So the databases, thinking of the clips, the different types of wiring harnesses, different types of hoses. You would not like to validate this every single one and every time again. So there is a possibility to store this in databases and just use it as an input over and over. And of course, last enables an interdisciplinary collaboration of teams within the OEM and the supplier at the end. So next, I will show a video how this could be working. So here you can just see an import of an infotainment system as a CAD file. For example, JT, CGR, whatever CAD file or whatever system you use. And then starting this request for the wiring harness out of our database. And then you can see that all the connectors, all the flexible parts are already connected, aligned to each other, and applied physically correct. So if we move, for example, the end, you can see everything is moving with its correct physics inside the simulation. And you basically have a two-click solution. And then you can, of course, start investigating further. Let's say a length is not optimized. You can do that in the system. And I will show that in a second video. Here, the wiring harness is already applied and already inside the tool. And now I would like to change, for example, the connector. Here, throughout the process, the connector might change. This will be the right one. Again, we will start the input of the database and searching on the database of the connector. Here, just typing in value, and we will now see that the input of the new clip, it might be quite small on your screen, but the decrease change on the clip, and this will be just now sent to IPS. You will see the update now. Of course, the flexible part connected to it also changed, and now you would need just to interactively vary the length to a best possible way. This is just now done by hand. Of course, you could go into detail with the capabilities I mentioned before and having a reliable result. So we are going from an iterative hardware-based process to a physics-based an integrated design and validation process in a virtual and digital way. Here's another example from BMW, which I mentioned before. On the left side, I want to speak about the conventional process, and on the left side, I want to speak about the conventional process, speaking on the early stage routing. And if we look at these connectors and, for example, the holders, how they changed and how the position changed until serious production routing, and of course, all the flexible parts connected to it, you can see that there, and this was just detected on the hardware, and this could, of course, lead to lead at risk of significant cost due to late design changes and going all the way back to the process as described before. So now have a look. Let's have a look at a new process on the right. Here. Yep, here on the right, marked with green. Here you can see a design of IPS cable simulation, which is the solution in yellow in 2015. And the series production layout and design at 2018, so 3 years after that. And you can see it's an almost identical layout. And if you think of the things I mentioned on the left, where you have all of these different changes, which at the end plays an important role of the flexible parts, such as the brake hoses and sensor cables in this case, you can really see the great improvement and being able to have a major routing concept 36 months before the start of production. So now I want to conclude. We are having an extremely enhanced productivity in the wiring harness development process with a comprehensive living digital twin. So we have a physical correct behavior of these flexible parts integrated into the customer's processes, ensuring functional safety requirements right from the start, having a major routing concept 36 months prior to SOP, and we say hardware-less development is possible. Now, I want to thank you very much for your attention. And if you have any kind of questions, of course, you're able to ask them now. But also after the presentation, you can contact us to this email address, and you can also request a live demo. Of course, during this presentation, I only showed videos, but I can also show you the same things live in the software. You can follow us on LinkedIn. And before I want to end my presentation, I want to mention one more thing. If you are interested in a more detailed presentation, we are having 2 webinars, actually 1 webinar with 2 dates, the 25th of May and the 8th of June, on the virtual design and validation of wiring harnesses and hoses with different contents, and it's just going a little bit more in detail in 1 hour. It's free of charge, and please feel free to just contact me, and I'm looking forward to start discussing. So thanks a lot. I just saw that I got a question. The name of the application, I think I mentioned it quite at the end, is IPS cable simulation.